one of the things we said about quantum mechanics is it's probabilistic. Okay, so everything in quantum mechanics is about probabilities and probability amplitudes. So in fact, the wave functions really are just telling us how likely it is to find a particle at a particular point in space. Okay, so if the wave functions represent probability densities or probability amplitudes, what we need is for those wave functions to be normalized. Okay, so basically the integrals over the whole of the wave function over all of space to be equal to 1. Okay, and that's because we're dealing with probabilities. Okay, you can't have a probability that's more than 1. If I want the probability of finding a particle at this point, it has to be normalized. Okay, so once we've solved the Schrodinger equation, we're probably going to normalize it. We're certainly going to normalize it, normalize our solutions to get good probability amplitudes. Right, so let's just talk more generally about what the Schrodinger equation is useful for, what quantum mechanics is useful for. So in chemistry and material science, we need quantum mechanics to be able to predict bond strengths. We need to be able to predict the geometry of molecules. And for instance, organic chemicals like drugs, it would be nice if we could simulate on a computer the interactions of those drugs with, for instance, a part of a receptor. Okay, it would be nice if we could use the accuracy of quantum mechanics to predict the properties of molecules. Moving on to sort of more physics-y type things. Semiconductors. If you're thinking about transistors in a microprocessor, transistors are small enough that they're within the quantum regime. Okay, and also band theory explains how, for example, a MOSFET junction works. What's actually going on as you charge up a device. What it's doing to the charge carriers, what the charge carriers are, what's happening to the charge carriers in the MOSFET junction. All of that can be predicted by quantum theory and predicted very accurately. Quantum field theory and nuclear physics, while not strictly what we're talking about in terms of sort of basic quantum mechanics today, is certainly quantum theory and is effectively a theoretical extension of everything we're speaking about. And more specifically to sort of DFT calculations, within the DFT calculation, although DFT is not strictly solving the Schrodinger equation, but we'll speak about that more later, pseudopotentials in plane wave calculations does involve a solution of a Schrodinger-like equation in a way that we'll also talk about. So the importance of the Schrodinger equation is sort of generally important for quantum mechanics, and it's also specifically important in the kinds of calculations that we want to do. Right, we've got to speak about a few more general things before we actually get to speaking about DFT, right? So spin in quantum mechanics. Spin is a distinct form of angular momentum from the orbital angular momentum L that we have in our quantum particles. So if you think of the analogy of a body orbiting a planet, for instance, and the moon orbiting the planet, what you think about is there's certainly some angular momentum in the moon orbiting, but also if our moon has some spin, okay, maybe it's better to think of the Earth orbiting the sun, right? The Earth is orbiting the sun, it has angular momentum, orbital angular momentum, and the Earth is also spinning. It has some spin. This is the analogy in kind of gravitational physics for spin and orbital angular momentum in quantum physics. It's not the same. It's just the fact that it was noticed originally when quantum mechanics was developed that these things involve angular momentum, but it's only an analogy. Okay, it's only an analogy. Where does spin come from? Spin is a relativistic phenomenon. Okay, so we do not get spin from solving the Schrodinger equation. You need to invoke relativistic quantum mechanics in order to derive spin. Okay, we're not going to do that. We're not going to do that today. We're just going to say spin exists, and once you know spin exists from solving the Dirac equation, then what you can say is, well, this particle has a spin index, say it has an up spin or a down spin, and we're just going to apply that. We're just going to say that particle has this spin. Okay? So just because spin comes from relativistic quantum mechanics doesn't mean that spin cannot be applied in non-relativistic quantum mechanics. Right. So what are particles more generally in quantum mechanics? Well, we can categorize quantum particles into basically two categories, fermions and bosons. Right? And effectively, the way we're categorizing them is in terms of their allowed spin values. Okay, so a fermion is allowed to have a half-integer spin. A boson has integer spin. Okay, and the main difference in terms of what we're actually interested in from a theoretical and from a computational point of view is in the wave functions that this leads to. Okay, in fermions we have anti-symmetric wave functions, whereas in bosons we have symmetric wave functions. Okay. Now, is it worthwhile trying to write that on the board? Maybe. So, if you maybe we'll just say it in words. I think we'll just say it in words. So if I no, I think we'll just move on. Okay, if you know this, you know it. All right. So what I want to do is move on to total angular momentum. All right. So angular momentum in quantum mechanics is summed vectorially. All right. So if we say we have an orbital angular momentum and a spin angular momentum for an ensemble of particles. So this is a vector of particles, and this is the orbital angular momentum of those particles, and this is the spin angular momentum of those particles. We can sum them as a vector to get total angular momentum. Okay, and total angular momentum is also a quantized number, just like the orbital angular momentum and the spin angular momentum. And the total angular momentum possible values range from the magnitude of orbital angular momentum minus spin angular momentum up to orbital plus spin angular momentum in steps of 1. Okay, right? We need to know this stuff if we're going to be doing kind of spin calculations. We need to know what we're talking about, what we're referring to when we say total angular momentum. Okay. Now, the reason I didn't say I resisted writing, for example, anti-symmetry on the board is because I think it's more natural to come back to that once we look at Hartree-Fock theory, probably after the DFT section, or maybe when we briefly look at spin-orbit coupling. I think we'll talk about that a bit more tomorrow. Right. Yeah. So composite particles is another thing to bear in mind, which is protons and neutrons. So, for example, in a hydrogen atom, we have a proton in the middle of the hydrogen atom, maybe also a neutron. But if we have a proton, the proton is composed of quarks. Okay, 3 quarks, and the quarks are bound tightly. Right? Now, what we expect is that a single quantum particle has is either a boson or a fermion. However, if you have 2 fermions with half-integer spin and you bind them together as a so-called composite boson, okay, they will act like they are a boson. Okay, so if 2 quantum particles are bound strongly, you can treat them as either a composite boson or a composite fermion, if that is what you're dealing with. Okay. You might say, why are we talking about this? Well, this actually is important if you're doing some kinds of DFT calculations in the future. So in certain spin DFT calculations, or quantum chemical calculations in general, we have to pay very close attention to what's going on in terms of the overall spin of the system. Okay, so not trying to sort of give you new ideas, just trying to really say this is the sort of thing that we need to keep in mind and pay careful attention to and know it exists. Right. So we will mention spin-orbit coupling in the beginning before we go on to DFT, but once we've spoken about different types of DFT calculations, we will also need to speak about spin-orbit coupling in a kind of more DFT sense. So effectively, spin-orbit coupling is the connection between orbital angular momentum and spin angular momentum of the electrons, at least in the kinds of systems we're going to be solving. Okay, so what's the mechanism? Well, as an atom orbits a nucleus, it has orbital angular momentum, it generates a magnetic field. Okay, and that magnetic field interacts with the electron's intrinsic spin. Okay, and this leads to splitting of energy levels in an atom. Okay, so this is fine structure from physics. Okay, so alpha, fine structure, and what the observable that's associated with, what we actually see in nature, is subtle variations in the atomic spectrum. Okay, so if we want to understand atomic energy states, atomic energy levels, we need to understand things like spin orbit in order to know what's happening in terms of the fine structure. Okay. Now, spin orbit coupling is associated with high atomic number. So we're talking about lanthanides, actinides, way down in the periodic table. Uranium, lanthanum, bismuth, lead, heavy elements, right? But even kind of late transition metal elements like palladium, platinum, we often need to consider spin orbit coupling because it starts to have a big effect once you get down to the high atomic numbers. And there's other things we need to bear in mind which are dependent on the atomic number. Right, Dirac notation. So we said that quantum mechanics exists in a Hilbert space, and in a Hilbert space we can represent vectors. Those vectors can be measured in terms of length and angle. We can take the norm of a vector by taking the dot product with itself and dividing by its magnitude. And all of this linear algebra, so, vector dot vector, for instance, divided by the magnitude of vector dot vector, right, is our norm of a vector, right? This kind of linear algebra, this notation, is not really common in quantum mechanics, right? So this is the kind of linear algebra notation you learn in mathematics. This is the kind of linear algebra notation you learn in, I don't know, mechanics. But in quantum mechanics, generally everything's written in Dirac notation. It's the same thing, it's just a different notation. So instead of writing a dot for an inner product in Dirac notation, if we write this as a V, it's just like this, okay? So you might ask, what is the significance of these angled brackets? The angled brackets, this one, okay, this is a vector, okay? This one is also a vector, but this is the conjugate transpose of this vector, okay? So if these are complex numbers, so we say, for instance, V only has one, V is a scalar, and V is, let's say, A plus IB, okay, is a complex number. This is that, right? And the conjugate transpose just means if we have a vector, and this is, I don't know, C plus IB, this is C minus IB, IB is fine, okay? This is also the row vector, okay? So this is transposed, okay? This is transposed. Okay, so this is column vector, this is the row vector. Okay, row vector. Number. Okay, so it's just linear algebra. So we can write inner product, but we can also write outer product. Okay, and so if you think about a vector, that normal vector notation, and you think about a cross product, okay, a cross product, what we're doing here, if this is, for instance, just AB multiplied by AB, okay, what we're doing is we're saying the first element of our matrix is going to be AA, then we're going to have AB, BA, BB, and we're going to get an outer product like that. Okay, in Dirac notation, our outer product is written like this. So if we're writing it as V, okay, just like that. Okay, that's all it is. It's a way of writing linear algebra, way of writing vectors. Okay. Right. So inner product, outer product. I suppose we should also say. Did I also write this in here? Maybe. Oh, matrix elements. Okay. So. Quantum mechanics is linear algebra. Okay, it is more than anything else an example of linear algebra. Okay, so everything exists in a Hilbert space. All state is written in terms of vectors in that Hilbert space, and the interactions that we prescribe in our quantum mechanics needs to be written in terms of those linear algebra operations. So. We can say the same things we said about our Hilbert space in terms of Dirac notation. Okay, so if you don't know this, you can just go back in the presentation. I'll send the presentation afterwards, and you can compare that everything we've said about the Hilbert space in linear algebra is what we're also saying about Dirac notation. Right. Okay. So there's a mistake there. Something's gone wrong with that equation. So what that was supposed to say, I think I've just accidentally written the LaTeX for the equation twice, but it was supposed to be Aij equals some vector I operator A J like that. Okay, so effectively all we're doing is we're taking a vector, multiplying it by an operator, and in fact we can, this whole thing is a matrix. Okay, so if we apply our operator to a matrix, to an element of our state vector, and then we take the resultant vector and we dot product it with another element of our state vector, what we get is the expectation value of ij. Okay, and the expectation value of ij goes into the element of the matrix Aij. Okay, and so the expectation value in general of a state is the average outcome. Okay, so if we have our matrix and we take the trace of that matrix, okay, we can find our expectation value of our operator. Right. We can do all kinds of operations in linear algebra, and we can write it all in terms of Dirac notation. So state transition probabilities. Yeah. Right. So now we've gone on our we've had our very fast tour of quantum mechanics, right? Probably not that very useful because we haven't gone into any detail, and we've had to gloss over a lot of aspects. But what we need finally is second quantization. Okay. Now, there's no point saying this if you don't know what quantum mechanics is, but basically, if we think of our potential and we think of our levels in that potential, and we've got some sort of I don't know, some sort of states in our system. Level, excited state. Okay. What these solutions to the Schrodinger equation are giving us are levels. They're where our particle could exist in terms of energy. Okay. So we could have a particle in our system in the ground state, the minimum energy. We could put it there, and it will occupy this standing solution, and it will have this energy. Or we could give it slightly more energy, and it will go into the next harmonic. Right? That's what's going to happen. What we can do is we can say, if we have these solutions to our system, we can have another number. Okay? And this number is how many particles exist in that state. Okay? Because all the solution to the Schrodinger equation is giving us is the potential kind of state that exists, all of the states that exist in our system, and it doesn't tell us whether we have a particle in that state. Okay? So what we can do is we can invoke a new number, which is occupation number. Okay? So in this case, if I label my states I, and I say that this is my 0th and this is my 1th state, what I can say is that f of I is going to be my occupation number. Okay, so in this case, if I have a particle, say, in the first excited state, then I can say that f0 is going to be 0 and f1 is going to be 1. Okay, and this number just represents how many particles are in that particular solution. Right. So, second quantization. I'm not going to go into very much detail on second quantization, but second quantization makes the study of many-body systems in quantum mechanics a little bit easier. Okay, I think that's sort of a simple way of saying it, and it's important for going beyond quantum mechanics towards quantum field theory, and it also plays a role more generally in statistical mechanics. Okay. What are some features of second quantization? Well, I think we can think of second quantization as kind of just a way of doing quantum mechanics, right? It's a formalism which has some rules associated with it, which has the same properties as normal quantum mechanics. I guess we can say that. All right. So if we look at the Hamiltonian formulation, and we look at a Hamiltonian of a many-body system. Okay. What we're looking at is a kind of, well, I suppose we could say a kinetic part and a potential part of our system. And every interaction in our system is dealt with by creation and annihilation operators. So if we have a state, okay, and we want to put a particle into it, we can use a creation operator to stick a particle into that level. Okay. If we want to remove a particle, we can use the annihilation operator to get rid of it. Okay. So you start to think, if I have this framework to deal with my system, I've got some systems and I've got some particles in those solutions. If I have more than one particle, it starts to become useful to have this framework to be able to put particles in and take particles out. Okay. But more usefully for us in terms of what we're going to be talking about in DFT, the main thing that we care about is the occupation number, the fact that we can label the states and say how many particles are going to be in a state. Right. So, yeah, I suppose quantum field theory, sure, but what we care about is condensed matter physics. Okay. Right. I think this is probably pretty much the last few sections on the introduction to quantum mechanics. Right. So we're almost finished. So basis functions. This is another thing we need to speak about before we start considering many body systems. We talked very briefly about choosing a coordinate system for solving the Schrodinger equation. Okay, so for instance, in the hydrogenic system, in the hydrogenic potential, it makes a lot of sense to choose the spherical coordinate system. Okay, trying to solve it in Cartesian coordinates is just masochism. Right? It's just painful for no reason. And once you go to many body systems, you want to do a similar thing. You want to be able to represent your system in terms of functions which in some way represent the shape of the system that you're dealing with. Okay, so an example of this is is if we have some atomic centers, say we've got 3 of them. We've got some atomic centers, and so each one of these represents a nuclear Coulomb potential. Oh, I don't need to draw it, right? Should I draw it? Right, we've got some nuclear Coulomb potentials. Now, we can say that these are bound by chemical bonds with some amount of strength, but in effect, it's the electrons are more strongly bound to their own nucleus. Okay, so in a sense, if you just draw a circle or a sphere around each one, they look quite a lot like just single atoms. Okay? Even though we're chemically bonded, they look a lot like single atoms. So if I solve this Schrodinger equation for this atom and ignore everything else, and then solve this one and then solve this one, anything else, any interaction between those atoms is effectively just a perturbation. Okay? It's small compared to the energy of the overall system. Okay? So it actually makes sense if I don't know the shape of the overall wave function of the atom, of the molecule, I can start to write the wave function of the overall molecule in terms of a linear combination of atomic functions. Okay? And so this is a basis, and this is why we said that in our Hilbert space we want our system. We want to be able to write a vector in our Hilbert space in terms of a basis. Okay? Because we can do tricks like this. If, on the other hand, we've got a crystal, okay, goes on forever to infinity in all directions. Now what we have is effectively a periodic potential, and our wave function is more likely to have a shape. Okay, screwed that up or whatever. It's more likely to have a shape which represents, which in some way resembles the crystal that the wave function exists in. The crystal provides the potential, and our wave function in some way resembles the crystal. Okay, our system looks like a bunch of atoms in space. Our wave function in some way resembles a bunch of atoms in space. A molecule in chemistry, right? So what this allows us, what using a basis allows us to do is to basically simplify the problem. Okay, you can use anything as a basis. You could just divide space. I could say that, okay, one of my wave functions looks a bit like, I don't know, like that. Okay, just drawing something randomly. Let's say it looks like that. Okay, I don't actually know that because I haven't solved it, but I've used some spectroscopic and some microscopic techniques, and I've viewed my wave functions of a molecule, if that were possible, and I've drawn them, and that's one of them. Okay? Now, how can I represent that? Well, I could represent it as a set of basis functions on each atom, or I could just divide space. I could just say, I'm going to have a grid like this. I'm going to have a grid just like that, and I'm going to say the value of the basis function in this grid on this grid point is some number, and on this grid point is a different number. Okay, this is a basis. Okay, it's a grid in space. So a basis is just a set of functions which allow me to approximate the function that I want, the vector that I want. Okay, and so you can see why it's important that we had those properties of the Hilbert space, because if we didn't, basis functions wouldn't exist. I suppose mathematically you can say you don't necessarily need your wave functions and your quantum mechanics to be in a Hilbert space. I think some people have done some research on representing quantum mechanics in Banach spaces, but let's forget about that, right? We only care about Hilbert spaces where we can have vectors which are separable and complete. Okay, right. So this is what we just said. Okay, in many body systems of atoms, the basis set that in general we'll use reflects the symmetry of our system. It's either going to be an atomic orbital basis set, or at least an atomic centered orbital set, which really just looks like solutions to our single particle 3D Schrodinger equation. Okay, or it looks like a plane wave because our potential is effectively periodic, infinitely periodic in space. Okay. If we add enough terms, okay, you can see that each one has got numbers associated with it. In this case, we've got the wave vector k. In this case, we've got our angular momentum, our magnetic quantum number, and our principal quantum number. If we add enough terms into these basis functions and add them together and use them as a linear combination, we can make the wave function of our many-body system in theory. Okay, so we're using them as kind of building blocks. Okay, I suppose a very rough analogy is if I want to make a building. Okay, I don't just find that shaped building and just put it down. Okay, it's impossible, right? What I need is to find some bricks and build up my building into the shape that I want based on those bricks. Okay, and these are the bricks we use to make our many-body wave function. Okay, or our many-body potential. Right. So choosing the right basis set really simplifies our problem, but it also I've just got to read this. I think I just said this. So choosing the right basis function basically allows us to get the solution more easily, but it also allows us to reflect the symmetry so that we don't need to use as many functions, as many building blocks to produce the thing that we need to compute. What I'm trying to say really is if I use a plane wave basis set to calculate a molecule and I use a linear combination of atomic orbitals to represent a crystal, probably I'm going to be doing more work than if I'd done that the other way around and used a more appropriate basis set in those two cases. All right, orthogonality and completeness. Okay, this is important. And it just comes back again to Hilbert spaces, right? Everything comes back to Hilbert spaces because everything is in a Hilbert space in quantum mechanics, right? So the basis set that we choose must be complete, okay, or at least to represent exactly our system, okay? So I'm just going to speak a little. I think I've only got a few more minutes. I'm just going to continue. So in this case, if we've got some atomic orbitals and we use them as a basis set, only when we have infinite harmonics are we going to go in our linear combination are we going to exactly represent the molecular wave function. Equally, only when we have an infinite number of plane waves are we going to exactly represent our crystal wave function. However, we only care about a certain accuracy threshold. Okay, so once you've represented, I don't know, the surface energy, some quantity, some observable. Once you've represented the surface energy to 3 decimal places of a Hartree, okay, or 3 decimal places of 1 eV, okay, at that point you're accurate enough. Okay, it doesn't really matter that you go to the 4th or the 5th decimal place. You know, if I say my energy is 1.2147, you know, etc. At this point, we really don't care anymore. Let's say this is EV. Okay, we really don't care anymore. So, although in theory our basis set must be complete, really we just need a basis set which is good enough to represent our observables below the threshold that we care about. Okay, so in practice, what we end up doing is just choosing a basis set which is good enough, right? Right, Fock space, yeah, non-orthogonal basis functions. One last thing. Is that the last thing? Who knows? Non-orthogonal basis functions. So our basis functions, we expect them to be orthogonal in general. Okay, so if I take one basis function, and I'm going to say that Actually, let's just write a different. Okay, so if I take a dot product or an inner product of a basis function with another basis function, what I expect is that it's orthogonal, so this is going to give me 0. Okay, so let's write this more generally. Let's write it as, I don't know, I and j. I would expect, if this is normal, if this is orthonormal, I'm going to have a delta function. So I expect that when it's the same, I'm going to have 1, and when it's a different basis function, I get a 0. Okay, effectively they don't overlap. Just like vectors, if my vectors are orthogonal, if I do the dot product of this one with this one, I get 0. Whereas if I take another vector which is non-orthogonal, the result is non-zero. Okay, but if I dot product this with itself, I get 1. Okay, right. But a basis set can be non-orthogonal. Okay, and what this means is that we effectively get, instead of this being a Dirac delta function, we get a matrix of overlaps. Okay, and so effectively our non-orthogonal vectors, okay, because these ones are non-orthogonal, right? Then they're between 0 and 1, and so our overlap matrix is a matrix of numbers between 0 and 1. Okay, and what we use that matrix for is the metric tensor. Right? Right. I think this is in a weird order, but so why do we use non-orthogonal basis functions? And the reason is because you're forced to. In condensed matter physics, in molecular systems, in crystalline systems, if we're using a plane wave basis set, plane waves are naturally orthogonal to each other. Okay. If we use a linear combination of atomic orbitals, Gaussian functions, Slater functions from chemistry, these are naturally non-orthogonal on different centers. So if you have, for instance, I don't know, an s orbital over here and a p orbital over here, and you bring those together and look at the overlap is between 0 and 1. They are non-orthogonal on different centers. Okay, so there is an overlap matrix associated with it. So we are forced to use non-orthogonal orbitals if we want to use a linear combination of atomic orbitals. Another thing, so physicists might arrogantly say, okay, well, in physics we just don't bother with such stupid things. We'll just do everything in plane waves, and that's fine. That's true, but there are orbitals there are basis functions in physics which are also non-orthogonal, like Vanier functions. So if you take your wave functions and you do a Vanierization process, so effectively you multiply by a phase factor which localizes your atoms and allows you to do things like transport properties, which of course are very important in solid state physics, then you get a Vanier basis, and the Vanier basis is non-orthogonal. Okay, so you can't always avoid non-orthogonality, and when you have non-orthogonality, you also have tensors. Okay, so our vectors have a tensorial nature. Okay, and this, so has everybody done general relativity in physics? Yeah, right. So effectively, if I'm just going to be, I'm pretty quick. I just want to get this bit finished, and then we will. All right. So in general relativity, or in tensors in general, if I have a vector, it either has a covariant index or it has a contravariant index, right? So if I say, for instance, I've got an index down here, or I've got an index up here, right? This is a covariant index, this is a contravariant index, right? So what does this mean? No. If I have a vector in space, okay, the vector is pointing from this point to this point. Okay, my space is in units. Okay, I could have my space in meters. I could have my space in millimeters. I could have my space in feet or kilometers. Right? But if I change the units of my space, if I multiply my space by 1,000, or I divide it by 1,000, okay, what I expect is that my vector from this point to this point still is that long. Okay, and so in order for that vector to be the same length, even though I've stretched my space around it or compressed my space around it, the vector has to transform in a way opposite to the way that the space is transforming. So as the space is compressing, the vector has to stretch by the same amount. As the space is stretching, the vector has to compress in order to maintain the same length. Okay? And that vector in space is a contravariant vector, right? A contravariant vector. And so in contravariant notation, that vector has an upper index. Okay? On the other hand, let's think of a room. Okay, so we've got a room here, and let's say we've got a temperature vector. There's a air conditioner here, so it's cold here and hot there. There's a temperature gradient from the air conditioner over to the other side, right? Cold, medium, hot, right? If I take the room and I squash the room, okay, what happens to the temperature vector? Okay, the temperature vector changes. So effectively, now the gradient of that vector is more steep, okay, because the temperature is changing from hot to cold over a shorter period of space. So the derivative is more steep, okay, and so that is a covariant vector. As the space changes, the vector also changes. Okay? And so we need the difference between contravariant and covariant vectors in a non-orthogonal basis in order to properly represent what's happening. Right? And so if you're a physicist, you'll be familiar with contravariant and covariant tensors from general relativity, because in general relativity, when we're trying to represent the expansion of the universe, okay, the space of the planets are moving in, the space that represents the gravitational field is changing shape, right? So for the physical laws to exist in that space, they have to transform with the changing shape of the space. Right. I think I've said that in words. Yeah, I think I've said all of that. Right. All I want to say is, how many slides have I got left on this? 3 slides. All right. Okay. So the metric tensor. So the metric tensor is the overlap matrix. Okay. What is the metric tensor? In tensors, the metric tensor is the tensor which transforms from a covariant to a contravariant vector. Okay, so if I take a covariant vector, sorry. If I take a contravariant vector and I multiply by the overlap, the metric tensor, this transforms this contravariant tensor to a covariant tensor. Equally, if I take the inverse, okay, this is the dual metric, which transforms a covariant tensor into a contravariant tensor. Okay? And everything can be written in terms of tensors. I can just say my state vectors are covariant. If I apply an operator to it, I have a dual covariant operator in matrix, which I've cast into matrix form, and my Schrodinger equation, or Schrodinger-like equation, becomes a generalized eigenvalue equation. So effectively, the only change is that I now have a metric tensor in my generalized eigenvalue problem, which means that in order to solve for the eigenvectors and eigenvalues, I need to solve a generalized eigenvalue problem instead of an eigenvalue problem, right? Okay. Everything's got to be tensorial. Right. Perturbation theory, no. Conclusion, I think, fine. Right. That's the end of the sort of basic quantum mechanics section of this class. Right. That bit is over. We're going to have a short break, and then we'll come back and we'll do some crystal type stuff. Right. And then once we've done crystals, then we'll do DFT, and then we'll be back on track, going on the things that we wanted to be doing. Okay, finished.